So, students, welcome back to this channel of mine where I try to make mathematics seem a bit more fun. And today we are going to begin a new chapter, second chapter of determinant. Determinants 2. Okay, in this one we'll talk about applications of determinants. Application of determinants. Okay, so first of all, I just want to apologize for one thing that if you want to understand why things going on the way they are, yeah, this video is not for you because I won't be able to help you with that because determinants and matrices and linear algebra in general uh, is a topic of 2D and 3D spaces, and if you really want to understand what is going on here, you need to visualize things. You need to see what is actually going on. What do these equations mean? What do these transformations mean? What do these determinants mean? And if you really want to understand that, then you will need high quality animation. And unfortunately, right now I'm not able to provide you guys with that. Okay, I would like to apologize for that. But of course, I know that there will come a time when I will be able to afford a smart board and help you guys visualize stuff. Okay, that is just has to be for the future. It will definitely happen one day. Definitely. Right now, right now, best your best bet would be just memorizing things. Things are not very difficult to memorize yet. You can do it easily. I mean, for the exam perspective, you can definitely get done with it. But if you really want to understand mathematics, then that is something I have been a huge advocate of. Like mathematics is not something like where you just memorize the formulas and learn their applications and uh, solve few questions using those formulas. No, mathematics is something that you visualize and you really have a grasp of what is going on here. Anyway, today we're going to be talking about two application of determinants. First one is calculating actually it's the failure of a education system as well. Like uh, our schools, at least government schools, don't have those facilities to help students visualize this stuff. Anyway, I won't complain. I will try my best to uh, at least be able to afford uh, to help you guys with those animations. Anyway, focusing on today's topic, calculating the uh, area of a triangle. Let's say we have a triangle ABC. The coordinates of point A are x1, y1. For point B, it's x2, y2. And for point C, it's x3, y3. Okay. Now, if we want to find the area of this triangle, area of this triangle would be half of modulus of a determinant, and the determinant would look like this. In the first column of it, we would have the coordinates of the x coordinates of these points. So those are x1, y1, sorry x1, x2, and x3. The second column would be y1, y2, y3. The third column would have three words, 1, 1, 1. Okay. Keep in mind that this is the sign of modulus function, and this is these two statements are indicating that this is determinant. Okay, the determinant we will be getting here. I've already told you guys what determinants are, and I've explained about what the identities of these determinants are. I know that over there as well, I have not been able to fully help you have a grasp of what's going on, because again you'll need high quality animations to understand what's going on here. You will need high quality animations to understand what is going on here. You would have to calculate this determinant here, and would have to take the modulus of that, because there is a possibility of negatives as well. So this modulus function would turn that into positive, and then we have to multiply that with 1 over 2. Okay. This is the first application of a determinant. The second one we'll be talking about today is going to be this. Solving a system of equations. A system of equations. Let's have a system of equation with three variables and three equations: a1x, b1y, c1z equals k1, a2x. I would have we're gonna plus signs in front of this uh, identities, in front of this quantities. A2x plus b2y plus c2z equals k2, and a3x plus b3y plus c3z equals k3. Okay. Now we have to find out a few determinants. Let's call them. Let's denote them by delta. Let's say the first determinant we have to find out here is delta. The determinant will look like this. We're gonna have the coefficients of the variables x, y, and z in the columns. Coefficients of x in the first column, coefficients of y in the second column, and coefficients of z in the third column. A1, A2, A3, B1, B2, B3, C1, C2, C3. Okay. Now we have to create three more determinants. I'll have to erase the things here. Actually, I can let them know here as well. Let's call the first actually the second determinant delta x. Here things would stay same as this one. Only difference would be that instead of having the coefficients of x in the first column, we're gonna have the values of these equations. Okay. So the first column would be k1, k2, k3, b1, b2, b3, c1, c2, c3. Third determinant, let's call it delta y. Then again, we're gonna replace the second column with this values, and the other two columns will remain the same. A1, A2, A3, C1, C2, C3, and in the middle K1, K2, K3. And let's call this fourth determinant delta Z. Here the coefficients of Z are going to be switched with the values of these equations, and everything else will remain the same. So this would look like this: A1, A2, A3, B1, B2, B3, and K1, K2, K3. Okay. Now value of x would be delta x over delta. Value of y would be delta y over delta. Value of z or z would be delta z or delta z over delta. This is known as the Cramer's rule. Okay. Again, don't ask me why things are going on over there, because you need high quality notions to understand 2D and 3D spaces, vector spaces. Okay, now let's talk about some important points. First of all, note this down here. Now, I hope you are done with that. Assuming so, I'm going to be erasing everything here. We'll have to check for a few possibilities. If delta does not equal 0, this means there's only one solution for the variables. This means that if the value of our determinant delta is not 0, then there can be only one possible combination of the values of the variables for which all of the equations will be true. That means if those linear equations, first of all, this solving this has to be a linear system of equation. Okay, I forgot to mention that. You have to keep this in mind. What do linear equations do? They create straight lines. So this means there's only one solution for the variables. This means that there is only one point in which all the lines are going to intersect with each other. There's only one such point. Okay. Now, if you guys are wondering that why is it that linear equations create straight lines like this, I would say that this was a topic of 11th standard. I would definitely explain this stuff in the future, but for right now, just keep in mind that linear equations create straight lines when they're graphed out. So they're plotted in a graph, in a vector space. Now, there is a second possibility in which the value of delta is 0. Now here we are going to have two sub possibilities. First of all, first one says where delta is 0 and delta x equals delta y equals delta z equals 0. If you encounter a situation like that, this means there are infinite numbers of solutions for the variables. So this means there are infinite number of points where the straight lines are intersecting with each other. Let's say you have two straight lines, each have their own equation. In such case, you will have two equations. Now, let's say this says that there are infinite numbers of solutions for the variable. That means these two straight lines are intersecting with each other in infinite number of points. Uh, First of all, it's a common sense that as the name suggests, straight lines are straight. Who could have guessed? This means they don't change their path while being plotted in a graph. This means the only way these two can intersect each other for infinite numbers of points if these two are the same. Only that way, only that way, these two would be able to intersect with each other in infinite number of points. If there's any other possibility, then either these two will intersect with each other for once and they will never meet again, or third possibility is that these two are parallel with each other and they would never intersect with each other. That means there will be no solution for the variables. If these two are intersected with each other for only once, then this determinant would not have been 0, it would have been non-zero. And we talked about the situation earlier. In that case, we would have only one solution for the variables. Now, this third case where these two statements, I'm just taking two statements. You can take as many as you want because it's a linear system of equations. You can this is a system of equations, so you can take as many equations as you want. Uh, uh, just keep in mind that when you are, if you want to solve a certain number of variables in an equation, you will have to need a minimum of the same number of equations as the same number of variables. Let's say in a system of equation, in a linear system of equations, you have three variables, so you need to have at least minimum three equations. 4 would work too, 5 would work too, but 3 is the minimum. If you have two variables, you would at a minimum need two equations. More than that would work, but not just less would not. Okay. Now talking about the third scenario, which is the second sub scenario of this second one, delta equals 0. The third scenario says, which is the second of this one, says that even if one of delta x, delta y and delta z are non-zero, there would be no solution for the variables. So it says that even if one of these three determinants, delta x, delta y, and delta 0, are non-zero, then that means there wouldn't be no solution uh, for the variables. which means that these two straight lines, unless we have two systems of equations, the straight lines created by uh, these two equations, two straight lines, would never intersect each other. And the only way that would be possible if these two are parallel with each other. Okay? I think I forgot to mention one thing about the previous scenario. If if the two straight lines are the same, that means the equations would also be the same. They might be in different forms. Let's say that the two equations are a1x plus b1y equals k1 and a2x plus b2y equals k2. Now, if there are infinite number of solutions for these two equations, and that means these two equations would be the same. That means a1, b1, a2, b2, k1, k2, all these things are arranged in such a way that these two equations will, when at the most simplified form, these two will be the same. For this case, uh, the only way two straight lines are only parallel to each other when when uh, their equations are the same. Ax, let's say both have ax plus by equals k1, and uh, the only difference would be this constant term. Second one would be ax plus by equals k2. The only way these two would be parallel to each other if the equations are the same. I mean, the coefficients for the variables at the simplified form are the same, but this constant term is kind of different. Only that way, their slope would stay the same, and on the same direction as well, uh, but not touching each other. Only that this is the only case when that would happen. Okay, if these two have been same lines, then of course those two would be parallel as well. If two lines are the same, then of course they are gonna be the same parallel with each other. Every straight line is parallel with itself. So this means here this constant term would also be the same its as at its most simplified form. Okay, this was it for today's video. As always, if you guys think that you have any doubts regarding anything I've told you guys today, you can let me know about that in the comment section. I will try to resolve your doubts. And until then, keep learning.